my name is Kathleen Franklin, and my final presentation is on the rotating snake illusion. Here you will see an image of the rotating snake illusion. I'm sure most of you have seen this illusion before. Let's get into the history of the illusion. It was first developed by Akiyoshi Kitaka in 2003. Since then, many others have copied or redeveloped the rotating snake illusion, hence why it is also known as Fraser-Wilcox illusion. There are colored versions as well as gray shaded versions. The rotating snake illusion is a completely static image. It does not move at all. It just appears to the viewer that it is moving. The motion of the image will stop if the viewer stares at just one point on the rotating snake illusion. Let's try it. Stare at one part of the image and notice the image stops moving. Now move your eyes across the image and the snakes will begin rotating again. The illusion motion is not caused by the motion of the image across an individual's retina. The movement of the eye is not causing the movement of the image. Instead, the image being in different positions on the retina is what really matters. Now you will notice that within the image, the discs each only rotate in one direction. Each disc is faithful to this direction. It will not switch directions. This is caused by the pattern of colors. The order is black, blue, white, and then yellow. Try reversing the rotating direction of a disc within the illusion. Now we are going to touch on 3 important facts about the visual system at work within this illusion. The first fact is that neurons fire rapidly whenever the image on the retina changes. Then they quickly slow down. Typically, you would think the slowing of the neurons would cause the image to fade, but that's not what happens. The fast initial firing rate allows visual perception to be fast. After the first initial action, the neurons go into what is called maintenance mode until the image changes again. When the rotating snake first projects onto a particular location on the retina, there's a lot of activity. The highest activity is at areas of high contrast, such as black and white. The lower activity is at areas of low contrast, such as blue and yellow. The activity levels experience different die-down rates. This difference causes a shift in the location of peak neural activity from black towards blue and from white towards yellow. The ratio changes, and this causes movement into the location of the center mass of the neural activity, which is detected by motion. Meaning the shift in the ratio of activity across the image generates the perception of motion, even though the sharp edges of the colored sections are completely static. Take a look at the image of the rotating snake illusion. The rotations of the disc seem to vary in speed slightly. The second point is that the visual system decomposes images into separate representations at a variety of spatial scales from coarse to fine. Motion is measured separately within each of these representations before they are recombined. In the rotating snake illusion, a viewer sees motion even though the crisp edges are not moving, because motion detectors at an intermediate spatial scales get activated, meaning that it is predominantly sensors at a coarser scale that generate the illusion of motion. The final point is that large-scale motions such as the rotating disc in this illusion have their own separate detectors at a secondary stage of processing within the visual system. These detectors look for larger patterns of motion in the image. These detectors are very sensitive. A small amount of illusion motion at many different places in the disc cause the disc to rotate entirely and not just the pieces. Now, do not think that the visual system is easily fooled, because that is untrue. The rotating snake illusion has been used as a teaching tool to learn more about how the visual system works. Also, please note, not everyone can see this visual illusion, because some individuals have a sharper visual system than the average human being.